So thank you everyone for being back in the room on time. So this is the second panel session of this afternoon. Thank you to all these gentlemen and women for sitting here for half an hour discussing the topic for this second panel session of pilots that are ongoing today in Europe. So thanks for the room for listening to the panelists. And so this is not Hystories research on the afternoons. As said, it is a panel session of other projects, other initiatives that are ongoing in Europe, and we are very happy to host all these panelists. I will present you afterwards. That's why I don't go through your names now. So this second panel session is about pilots. A short reminder of where we are on only pure hydrogen storage in the world, actually. So we've got, as you know, probably there are 6 historical caverns storing hydrogen, not hydrogen as a green as a gas used in the net zero transition of the energy systems. But as a gas used as a feedstock of the petrochemical industry, but it is still the same, hydrogen stored in salt caverns for more than 50 years sometimes. There are 2 industrial caverns that are being leached today, actually, in the US. So it's not a plan, as someone says, it's real drillings, as someone would say. So you see here, this was in February this year, a well being drilled for developing an industrial scale salt cavern storing hydrogen. And there are pilots, especially in Europe, a lot of pilots. There are, I hope I did not forget one, maybe, so please excuse me if I did. But there are, I think, 5 that are either under construction or testing in salt caverns: HyStock, HyPSTER, H2Cast, HyCav Mobile, and HPC Krummhörn. There is one in depleted field, sun storage, and there is one lined mine cavern, hybrid. So we are very happy to have this afternoon 4 of these projects being represented. So they will present you the project, and we also want to look at the list, to hear and to discuss the lessons we can learn from all of your pilot projects that you and your company are developing, and try to wonder why do you develop these pilots? What do you want to? What goals do you want to reach? What achievement did you reach in case you already did these pilots? And also why? So is that to convince people, to convince investors, internally your own staff, to convince your country's regulator, general public and society? Is that because there is a real technical reason? Because hydrogen is really a different molecule. We discussed all the microbiological activity thing a lot, for instance, here. Is that just to gain maturity and to develop the ecosystem on hydrogen, etc.? So why did you develop these pilots, and what did you learn? This is the main questions we want to hear about this afternoon. So we'll start with Eddy Kuperus. So I will introduce you. So Eddy Kuperus holds a position as a business development manager in hydrogen storage NV Netherlands Gasunie. He is an experienced petroleum engineer and has been active in underground gas storage projects in salt caverns and in porous media since 2008.
Well, thank you.
You can move the slides with this.
Good, thank you for the possibility to talk about our project. First of all, I work in Gasunie. And Gasunie is a European infrastructure company, or actually a European energy infrastructure company. We want to be the connecting factor in the energy system. So that means that we are involved in transport of methane, but also in supporting activities like storage of methane, importing of methane. But as we realize that methane is not the future, we have a focus on new energy. So that is a activity that we have been focusing on now for the last few years. And that means that we are active in developing a hydrogen transport system. We are active in hydrogen import stations, but also in hydrogen storage. And we do not want to be a player, only a player. We want to be the company that promotes and pushes towards a green energy system. So we are not a follower, but we are a starter and a front runner in our activities. So for hydrogen underground storage, we have an ambition to develop and manage large-scale underground storage, and in a modular way. So that means for us in caverns, because caverns can be relatively easily modularly developed. And for that we are working on a project called HyStock. HyStock is a project in the Netherlands where we develop a surface facility and 4 caverns, of which 1 cavern is already ready to be used for hydrogen storage. And we are now in the detailed engineering phase of our surface facilities. And our plan is to be ready for hydrogen storage in 2028. And then the other 3 caverns will follow in the years after. And we are also involved in the project H2Cast, which is a pilot project in Germany, in Etzel, where with a consortium of companies, hydrogen will be pumped from one cavern into another. So that makes it possible to make multi-cyclic testing and to test the effects of this multi-cycling on materials and on the behavior of the hydrogen, pollution of hydrogen, for instance. In the HyStock project, we have executed a demonstration project, and we called it A8 demonstration project. That is named after an existing borehole, which we have completed to a storage cavern. And this project started this pilot project started in the first quarter of 2021 and was finished last year. And what we wanted to achieve was twofold. The first work package, which was executed together with TNO, was to develop a generic risk identification methodology, and also to develop a generic workflow to quantify the risks of hydrogen storage. So those two topics have been also the basis for the design of the real test, which was in the work package 2. There we had 3 objectives. The first objective was to design and to execute an integrity test with hydrogen to prove the tightness of the last cemented casing shoe, of the casing itself, the wellhead, and the salt. And the second objective was to prove the suitability of materials. That means materials like salt and cement and steel, but also the components like a downhole safety valve and tubings. On top of that, we wanted to prove that we can operate a salt cavern filled with hydrogen. So that means we have executed measurements with Y-line. We also executed snubbing operations. We have used E-line. We have tried to execute the standard operations that you need for operating a hydrogen storage facility, but then under hydrogen. And on top of it, we wanted to prove that our operational procedures would be applicable for hydrogen. And the generic idea for all those steps was that the knowledge that we had in operating methane storage would also be applicable for hydrogen storage. That was the generic idea. And we only changed or adapted where we thought based on our risk assessments where it would be required. And the last work package was to collect samples to, for instance, assist the test on microbial growth or geochemical reactions. But also we have installed a lot of little samples of materials, and they were under hydrogen conditions for 9 months. Then we pull them out and send them to the laboratory to investigate if the material characteristics changed due to the hydrogen or not. So all that program has been executed successfully, safely, no incidents. So that means that at least the operational procedures and the materials functioned as we expected. For the laboratory and material testing, it's still under in progress, so we have no final results yet. We expect to present some results by the end of this year, yeah, so that is what I wanted to tell. Yeah.
Thank you, Eddy, for the presentation of this HyStock project. So probably the first one that has injecting pure hydrogen in a well in the European Union since UK left the European Union. The second project will be presented by Stephan Bauer. Stephan Bauer studied civil engineering at the University of the Natural Resources and Life Sciences, Vienna, and graduated in 1996. After several years working as a project manager in civil engineering companies, he joined RAG, Austria. In 2008, he managed several projects in the gas storage infrastructure expansion program. In 2012, he started with the development of interseasonal renewable energy storage solutions. He was responsible for the underground sun storage project 2013-2017 and the underground sun conversion 2017-2021 projects. Since 2018, Stephan Bauer is head of Green Gas Technology Department at RAG, further developing interseasonal renewable energy storage solutions. So it's not microbios anymore.
Yeah, thank you, Arnaud, for the kind introduction. Yeah, so I'm the odd guy that is heading for hydrogen storage in depleted reservoir. Regarding the risk assessment done by Martin, our reservoir is the full risk reservoir. It's rather shallow, low salinity, low temperature. But I will try to explain what puts us in this situation that we go for such a project. Let me start with a few words about RAG Austria, the company I work for. We are one of the leading technical gas storage operators in Europe. Some facts and figures are stated on the slide. Unload capacity 30 gigawatt, so that's quite a number in the European energy system. And even with the existing fossil-based energy storage business, we support the development of renewable energies in Europe, because every time when there is the so-called Dunkelflaute or there is not enough energy in the system, someone needs to provide the energy, and that is provided by storage facilities in the first place, and then of course converted to electricity and so on. But of course, our focus for the future is to further develop our services to provide seasonal energy storage solutions for renewable energy, for a full renewable system. And that's what we did in the past, and I will show our track record. Why depleted reservoirs? First of all, RAG only operates depleted reservoirs, so we have no other choice. That's the easy one, yeah. But if you look at the European system, 75% of the volume is provided by depleted reservoirs. And considering the fact that hydrogen has much lower energy density, we need volume to store renewable energy in the future. So I think there is no other chance that to also look at, I'm not against salt currents, no problem with that, but I think we have to also look at depleted reservoirs rather on short notice and not wait till the end. Yeah. Besides, there are several areas in Europe where there is no option for salt currents, and there is only depleted reservoirs, like in Central Europe. Here's our track record. We are dealing with hydrogen in the subsurface in depleted reservoirs since more than a decade now. I won't read all the projects to you, but what's important to know is that since 2015, we have practical experience about the behavior of hydrogen in depleted reservoirs. We started operating in 2015, at that time with admixture of hydrogen to natural gas and storing 10%, 20% of hydrogen in depleted reservoirs. And the experience we gained, and also lots of laboratory experiments and other surveys, put us in the position to start a new project, or we have started actually the Underground Sun Storage 2030 project, and that is the pure hydrogen storage in a depleted natural gas reservoir. Here's the setup of this project. It's a nationally funded project with a strong Austrian consortium. A lot of Austrian energy utilities, industry supports this or works together with us in that project. The concept is quite simple. We have a power-to-gas procedure at the beginning. A compressor puts the hydrogen to the reservoir. And once we take the hydrogen out again, we have standard operations of like every gas storage facility has, a drying unit, free water knockout drying unit. And then we consider three different options of how to deal with the hydrogen. One is admixing to natural gas, replacing natural gas in the public system. That's rather the way, because there is not an existing pure hydrogen infrastructure there at the moment. So we have no other choice to admix to the natural gas system. But then we also test a purification system to to upgrade the hydrogen to fuel cell quality again, because when you store hydrogen in a depleted natural gas reservoirs, you will get hydrocarbons when taking the hydrogen out again. And so you have to look for a purification system. And the third option is to directly make use of the gas mixture, you might say, with a certain amount of hydrocarbons, and to utilize this hydrogen in industry where the quality of hydrogen is not much of an issue. On the right side, you can see a few facts and figures about the project. Operating volume 1.2 million cubic meters. The parameters of the reservoir itself. We have a very low salinity, as I said, a temperature of around 40 degrees, a 2 megawatt water electrolysis to provide the hydrogen. And just a few weeks ago, we celebrated the inauguration of that facility. We had local politicians from Austria. We had also an open house party for the neighborhood. It's always important to somehow integrate them and communicate with them. And that works out really fine because the neighborhood really likes the project because they think it's important for even their future. Yeah. Okay, here are a few pictures of how the facility looks like. It's a nice area in Austria, a touristic area. Here you have one of the lakes with lots of summer tourism. In our terms, a rather small facility, but it has all the equipment a typical storage facility has. Talking about the necessary equipment. We have the grid connection, we have a trafo station, a transformer station, we have the electrolysis, we have the compressor unit, we have the well, which was an existing well. We just recompleted it by adding a subsurface safety valve, but the steel qualities are the same like every other natural gas well, so not much of a change. We have the purification, free water knockout and drying unit and the purification system. And we have a roughly 8-kilometer pipeline connecting this facility to our commercial facility where the utilization of hydrogen will take place either in a CHP or, as I said, at mixing it to the natural gas system. The objectives of that project, we want to develop an interseasonal energy storage solution. We want to prove that it's feasible to do that in a depleted natural gas reservoir. Of course, it's always interesting to compare our results with lab experiments, with assumptions we did before. And also this use case development, use case considerations will take place together with the consortial partners. The title of the session is "What can we learn, or what have we learned from pilot projects in Europe?" Well, we are ready for operation almost. One of our suppliers has to do some homework, but commissioning is almost completed. So we have not gained any data yet from how the hydrogen behaves in the reservoir, how much we can take out again, what's the quality and things like that. But the learnings are already there. We could prove that it's feasible to design and to construct and to commission a facility like that. It's on one hand, it's a new pathway, but on the other hand, you still rely on existing standards, existing equipments. It's not much of an issue to specify all the equipment and to get it on the market. It was also good to see that with all the approval process by public authorities, it was not much of an issue. Yeah? Even though that the existing regulation is not really made for hydrogen storage in Austria yet. I guess in several other countries in Europe it's the same. But in our discussion with the authorities, it was still possible to find a way how to get this done, and also to showcase what needs to be done to roll out this in a commercial way. Yeah, and with that slide, I'm done, and hopefully we can discuss later on. Thank you.
Thank you, Stephan. We will move to the presentation of the third pilot project this afternoon by Grégoire Hévin. So Dr. Hévin is a geomechanical engineer and expert in underground gas storage in salt caverns. After a PhD in geophysics, he joined Gaz de France, then Storengy, to work on the salt caverns. Grégoire has supported gas storage operators for more than 20 years in the domain of tightness test, gas filling, cavern volume evolution due to salt creep, subsidence, abandonment of gas storage salt caverns. He was underground project manager for the developments of Autrive site. He also had research and development activities on the thermal and mechanical behavior of rock salt. Today, he is the scientific coordinator of the HyPSTER project, a pilot experiment of hydrogen storage in a salt cavern.
Thank you, Arnaud. So the HyPSTER project, that means hydrogen pilot storage for large ecosystem. HyPSTER is not because of my verb. Even if I like to play with this name of project. So the project started in 2021. Probably finish in 2024. Initially, it was planned to finish in 2023, but what we learned from the pilot, sometimes it's longer than we imagined before. The idea is to develop an experiment in a real salt cavern, which was available in the Étré site in France. Étré is a site, it's gas storage, natural gas storage in salt cavern. You have an idea of the budget also, and on the right, you can see the different partner of the project. With Storengy, there is ESK in Germany, Armin, and École Polytechnique, Boire Consulting, Ineris, Innovin, Element Energy, Equinor, etc. And some strategic partner for different equipment. This project is supported also by the Klein Hydrogen Partnership, like Hystories. Yeah, okay. In fact, we have two projects in one. The first one is to have a renewable hydrogen production with an electrolyzer of 1 megawatt. With electricity and water, we transform water into hydrogen and have transportation by tube trailer. And on the other part of the project, it is pilots of storage in a small salt cavern, in which we will do tightness test and pressure variation cycle. Just to show you the map of the facilities, in blue you have the platform from the H2 production, and in green it's a platform of the cavern, very near the natural gas storage station. You can see here in orange. This is the diagram, the layout of the hydrogen production platform. In red you have the electrolyzer and local for supervision, electrical substation, a small buffer tank to be sure to have a constant pressure in the system, and a compressor to compress the hydrogen to tube trailers. And you can see some picture of the installation. Today, all these civil engineering are finished. So everything is ready to receive the equipment. So you can see the firewall, real firewall, not informatic firewall, and a part of the electrical substation. On the storage site, this is a picture with the rig, the machine we used to set new equipment in the well. It was in April, March and April. So today we have this new completion, new equipment adapted to hydrogen. You can see the wellhead, which looks like a classical wellhead, but it's wellhead hydrogen ready. Today we have nitrogen in the well in preparation to the tightness test. But we are building the surface facility to manage the test. So we are not exactly ready to do the test, but the nitrogen is already in the well. So this is a diagram of the surface facility, and you can see that there is the well, the cavern. We will inject hydrogen in the well, and we also work with brine to withdraw brine when we inject hydrogen first, and after that to create pressure variation by injecting a withdrawing brine. So we have different reservoir, different storage, brine storage. You can see on the right the picture of this storage, and also the brine skid with the pump and with all the equipment, sensors and so on for the test. At the end of the experiment, the hydrogen will be withdrawn and vent directly. This is just to show you what we plan to test in the cavern. In fact, the idea is to fill the upper part of the cavern with hydrogen and to keep the rest of the cavern in brine. And we have a central tubing full with brine. And the idea is to simulate the hydrogen operation by injecting brine and withdrawing brine, and create like this. Yes. So we plan to have small cycle superposed to large cycle of pressure, and to repeat the operation about 100 times, and to finish to have large cycle of pressure and the final withdrawal of hydrogen. Yeah, I think it was the last slide.
Thank you, Grégoire. We will continue before the question with the last pilot project that will be presented this afternoon. It is the HPC Krummhörn project. It will be presented by Miriam and Annette. So Miriam Panhofen studied mining engineering and has worked in the energy industry for 20 years. During this time, she has managed a variety of projects in the field of natural gas storage technology. For some time now, she's been developing concepts for underground hydrogen storage at Uniper, and thus deals with a variety of issues around the topic of R&D hydrogen storage. And Annette Lenze studied geology and graduated with a PhD at the University of Bochum. Since 2008, she worked in the gas business for almost 10 years at Uniper Energy Storage. Currently, among other projects, she's working as backup of the subsurface project manager in the pilot project HPC Krummhörn.
Yeah, thank you, Arnaud, for the introduction. We will split this presentation into two parts. I will start, and then I will hand over to Annette. Oh, you can't see it there. Okay. Yeah. So we will talk about HPC, Hydrogen Pilot Cavern. And the name is a little bit easier to pronounce than Krummhörn project, but it's pretty much the same. Yeah. So for those of you who are not that familiar with Uniper Energy Storage, where Annette and I work for, belongs to the Uniper Group, and we are the largest gas storage operator in Germany and also in Europe, one of the largest one. We have 9 gas storage facilities in Europe, most of them in Germany, but also in UK and in Austria. We are connected to 4 market areas and have a gas storage capacity of 80 terawatt hours in total. So the HPC project, what is it about? We want to build and demonstrate a hydrogen cavern, actually a very small one. And we want to gain all of the knowledge which you need to know when you store hydrogen. So, but only on a small scale. Of course, all the technical details you need to know, but also the permitting process, because everything is new. You can't go to the mining authority and let them know we want to store hydrogen. You have to develop it also with them. You need to do a lot of investigation of materials, like this morning we had the presentation from Bernd, and yeah, you can't take anything out of the scratch. You need to think about everything, so it's quite interesting. Sometimes it's frustrating, but yeah, we enjoy it. Oh, okay. And where does it take place? In northern Germany, close to the coast, we have a facility where we have 3 caverns and also 1 well. And for this project, we used the existing well. And as you can see, we have started with the permitting process already last year, and it's still ongoing. The design phase is also almost done. The procurement phase has started, and yeah, there's still some parts missing, so ongoing. Construction has started as well. And if we keep the fingers crossed, in the beginning of next year, we will start to fill the hydrogen into the mini cavern. And when I say mini cavern, it's really small. It's about 1,000 cubic meters. It has a pressure of 70 to 270 bar. And we expect a capacity of 700 megawatt hours and a working capacity of gas of 500 megawatt hours. So that we have a flow rate of 1,200 cubic meters an hour. That was the general overview and the introduction, and now I will hand over.
Thank you. Thank you, Arnaud, for the introduction. Welcome. Yeah. Now I come to the technical part. You see the different technical project phases in the beginning. Now we only have a well. We don't have a cavern yet. And the well, as you see on the left-hand side, is equipped with a conductor pipe, with an anchor pipe and the last cemented casing, and is filled with brine. The well is drilled in 1994 down to 1,800 meters roundabout. And the open hole part is about 300 meters long. You can't see it on this picture, but it's like this. And when we looked at the cased hole part, we measured everything. I will come to this into more detail later. But we found out that the lower part, the open hole part, was blocked with cement and salt. So we decided to re-drill the open hole part. And that's what we did already. Then we inserted the leaching pipes, the 2 leaching pipes you see on the next picture, leaching wellhead. And then with these leaching pipes, we started to do the 2-phase pressure test with a medium of nitrogen first, and then with a medium of hydrogen. That is ongoing at the moment. I will come to that later. After the leaching phase, when we have this small cavern we want to fill, we add the completion, the production completion. We have these completion string installed with a packer and also a subsurface safety underground valve and hydrogen-ready master valve at the top. Then, as Miriam said, we plan to fill the cavern with hydrogen in the beginning of next year. We also insert a deep brining pipe, as you can see on the last picture, so that when we fill the cavern with hydrogen, we get the brine out at the same time with this deep brining string. And after the brine is got out of the cavern, then we get the deep brining string out as well. Mm-hmm. And here, as I said, I come to more details. We looked at the cased hole part. We did the inspection of the wellhead components, and we saw that they were not H2 ready, so we had to exchange them. We did several casing runs, logging runs in the casing, like a caliper run, a USIT run, a CBL, VDL run, to see if the casing is in a good situation, if the steel is good and not corroded, and also if the cement is well bonded to the casing. That has all been done, and it was successful. The casing is in a good situation. And meanwhile, we did some laboratory investigations as well on steel and cement. And on cement experiments, we already have some good results for the first 3 months test, but it's still ongoing for a longer time. Since there are no standard procedures, as Miriam said, we involved a third party, the DNV, that is verifying all these procedures and test performances that we do. All this investigation of the last cemented casing has to be done, of the casing at all, has to be done to see that the last cemented casing can work as a second barrier, which is important for later. Mm-hmm. Next slide. No. Here you see the operation of the open hole, since we had to re-drill it to re-access the borehole that was plugged. We had to use this for missed the word. The what one? The rig, sorry. Yeah, you see the rig on the left-hand side there. So, and after that, after we re-drilled the whole open hole part, the 300 meters, we did a borehole survey. And as I said, we installed the test wellhead and the test and leaching wellhead and the tubings. Up front, before we installed that, the H2 readiness of this equipment was proven. Next slide, please. This was already done, and now we are at the moment at this phase. We do the two-stage tightness test. We already did it with nitrogen. That was successful. We've proven that the last cemented casing is tight for nitrogen, and at the moment we are testing it for hydrogen. We have hydrogen in the well, only to that part, as you can see here, below the casing shoe of the last cemented casing, and it's pressured up to 208 bars, and it's there since Monday. So it's filled up to this pressure since Monday, and now we have to see if the pressure is holding that standard. So it's ongoing, and all these pressure test procedures and criteria are also verified by the DNV. Upfront, before we did these pressure tests, we had a HAZOP meeting and an operational training for handling with hydrogen, since this is dangerous, of course. Next one. And why do we do this? That was the question in the beginning. We want to get information about the material, the steel and the plugs and everything, the pucker, the subsurface safety valve. Then we want to see if the services are ready for hydrogen, to work into hydrogen and the hydrogen conditions. We want to see afterwards what the quality is like after the withdrawal of the hydrogen. Then we want to learn something about the thermodynamics and learn for our simulation of the process parameters, and also learn something about the rock mechanics. Next slide. Here you see the surface installation as they are planned. They are not in place at the moment. What we have is on the left-hand side of the picture, you see the wellhead, which is still the testing wellhead at the moment, but it will be replaced afterwards. We have the field pipe that we can use, and then we are planning to have an electrolyzer in place by a partner. With the power. Ja, das ist eine gute Idee. Wie geht das denn? So. Ja. No, I have to point here, sorry. Oops. And on the other hand, we could have hydrogen injection via trailer like we did for the pressure test at the moment. This is the hydrogen injection. Then we have in the middle part, we have the hydrogen treatment. After we have the 2-year test. When we fill the cavern with hydrogen, it stays there for 2 years. And after that, we will get it out and have a hydrogen treatment here then in place. It's not there at the moment. And then we have 4 different options what to do with this hydrogen. We will for sure have an injection to the transmission grid. We could bring it into hydrogen trailers. We could use them in the fuel cell power generator, and also for hydrogen filling stations. For this procedures, of course, it has to have a high quality, and that's something we don't know so far. We have to see what the quality is like, and therefore we have to have the treatment of hydrogen afterwards. Yep. That's it. Thank you very much for your attention.
Thank you, Miriam and Annette. So now we will try to start discussing this project. I may start with the first question, and then I hope there are a lot of questions in the room and online. So can you explain us the big bottlenecks you faced during this project, and what were the main difficulties you had when wanted to demonstrate something being underground storage? What are the biggest difficulties?
What we developed so far is that it's kind of hard to get answers to the question like what kind of material can we use. Like I said, the permitting process, nothing is known. You need to work out everything together, like with the mining authority and everything. That takes a lot of time, and sometimes it changes your schedule. Yeah, that's kind of tough, I would say. Anything else?
So I can be next, no problem. I think what is definitely a hurdle at the moment is the lack of operational experience. So that we should overcome by operating this facility, and definitely also. Let's say, regulatory framework that somehow opens a possibility for a business case. Yeah, we're looking at that in parallel, of course, and it's rather difficult at the moment. From a technical perspective, or from our technical perspective, we did not have so many troubles in let's say. Designing the facility, including the well, but we have a lower pressure than you have, and that might be an issue. Yeah, so from a practical perspective, we have quite good experience to the point where we are at the moment.
Okay.
On my side, I think what was difficult at the beginning, of course, was to find the good material and to find the good technical element to set in the well, to prepare things, to design, to discuss with the suppliers. But finally, we imagine it could be difficult, but finally it was not so difficult. We have very good contact with the supplier, and we are probably in the good time for them to develop new equipment adapted to hydrogen. So it was a good experience to discuss with supplier, to find solution, to adapt eventually things. And today, I can say that on the market you can find equipment for hydrogen to have a good completion for hydrogen in a well. We had also this question of administrative experimentation, I should say, because when you with this pilot experiment, you are in something new. On the paper, everybody said it's okay. Administration, yeah, it could be possible. And when you did, so now I need an authorization. It's not so simple, in fact. So it was a long discussion with the help of our partners to propose things to adapt from the existing rules, but there is no rules for hydrogen. And so to find a way to propose the good file, the good information document, impact studies for hydrogen, and to convince administration that it's possible to only to make the test, but also to work on the idea to have a real storage, hydrogen storage. And so I think I can say that today we are a clear view of the administrative process to develop an hydrogen storage in France. Of course, it's very national because the different administrations in Europe are different, so the approach could be different. But today in France, it seems to be clearer than at the beginning of the project, for sure. So it's the last point. I think it's linked to the timing, and I think it's a real bottleneck today. We imagine that we need a long time to develop hydrogen storage because it's industrial object. You need time to leach a cavern, you need time to set a completion, you need time to fill the cavern with hydrogen. So we want to be in time ready, but the rest of the system, the hydrogen production, the hydrogen transportation is not really here. The hydrogen consumption is not here. And so when you need large quantity of hydrogen is difficult. For our project, we imagine to fill the cavern with only 3 tons of hydrogen. When I met a possible supplier of hydrogen if we had a problem with our electrolyzer and said, I need 3 tons of hydrogen. They say it's difficult because in your place, you need all my capacity of hydrogen production and transportation by truck for 3 weeks. And I have already my clients. So I cannot give all my capacity for 2 weeks just for you. And I'm not speaking of a small company producing hydrogen. I'm speaking of big company like Air Liquide or Linde. And they say, no, we cannot. And we cannot because the hydrogen market today, finally, is very small. And we have not the capacity for one shot to say, yeah, 3 tons in 1 week. Okay, no problem. So I think finally we finished to find a supplier say yes, okay, we can do it. But I think for porous media, if we want to do a pilot, the quantity of hydrogen will be very, very larger, and it could be a problem. And if we wait that all the hydrogen chain ready, we will be late to develop the storage. So it's something a little difficult to have this, to be in the good time scale.
Yeah, thank you. So I think we started, I think, as a first pilot project. I think after we had convinced our management that it was a good idea to introduce or to start this pilot project. The most difficult part was to get components from suppliers and to convince suppliers of well components that their equipment would be used in a hydrogen test well. Because the suppliers, they claimed, well, the materials is not designed for hydrogen, so we are not sure if we can deliver you a component which you can put in your well. So that took quite some discussions with suppliers, but in the end we managed. Authorities were very keen on following what we did, and they supported us in what we did. They overlooked our processes, and they also learned from what we executed. And we were lucky. Our project, the HyStock project, with testing in a well, started in 2021. But in the years before, we had a first HyStock project, which was the construction of a 1 megawatt electrolyzer. At that time, the biggest electrolyzer in the Netherlands. And so we could supply our own hydrogen, which made it a little bit easier but yes, indeed, I see the problem of today that it is difficult to purchase enough hydrogen to execute pilot projects.
I would say that's definitely true what Greg said, that it's difficult to get some hydrogen since we only used hydrogen so far for this test, for this pressure test. So we needed only a little bit of hydrogen, and that was a problem, that we were said that, we can deliver it now, but the next delivery will be 2 weeks later. And this is something that's really a problem if you want to go on in your project and want to reach a goal that you want to start with the test by the end of the year or at the beginning of next year. Yeah.
Thank you. No, thank you. Thank you. Sorry. Nope. No, that's a lot of information that you already gave. It's very interesting. I mean, it's hard to maybe to catch all of the experience, but I heard like you face material selection problems or difficulties in the HPC, in HyPSTER, in HyStock too, and I hear that you're quite confident that now it's much easier to procure hydrogen completion elements. That's what you said, at least from what I get. So it's the first very good point, I think, that that these pilots are bringing to this industry. I mean, it's a huge change, and we're seeing that, and we've been seeing that between the beginning of Hystories and end of Hystories. It was also, I think, a very different maturity for a supply of hydrogen-ready equipments. And I'm also surprised by what you said about the difficulty of getting hydrogen for a few tons pilots. I mean, we are discussing deployment of 400 soul cavern equivalent in Europe by 2030 sometimes, of 3,000 tons each. And we hear from the experience over the past few years that you've got difficulties to procure a few tons of hydrogen. So it looks very surprising to me as well.
For the suppliers and the material equipment for completion, we took benefit of the global interest in hydrogen too. I imagine if we are the only company in the world interested to store hydrogen, the supplier have not the same motivation. Today, there is the idea of large development in this domain, so they are ready to make effort and so on. And it was very interesting to discuss with them because the idea, they are ready to develop things and to test things and so on. So it was also in this global interest in Europe, but in the world, in hydrogen, that we have this benefit. It's not the same thing for the hydrogen suppliers today.
What I observe is we hear a lot of discussions about the hydrogen backbone in Europe and development of hydrogen infrastructure. We do not hear so much about the development of hydrogen storage. And I think, well, of course, it doesn't make sense to develop storage facilities without pipeline infrastructure. But it's also the opposite, the other way around. I mean, it doesn't make sense to develop a pipeline infrastructure without storage facilities. That will not work. And so I think we need to have an eye on both developments, and it should be a mutual development.
Yes, I mean, the deployment at the European scale of these infrastructures, post-transportation storage is, I mean, it will be a focus of tomorrow's presentation more maybe, so, but it is, and it needs 10 years to develop. I think it's what Jorgo said when he said there is this chicken and egg problem that we face. We've got infrastructures that takes 10 years to develop. There's no market now, but when there will be in 10 years, according to forecast by the European Commission, for instance, it will be too late to have infrastructure ready if you decide that in 10 years. So yes, this question is key, I guess, in this infrastructure business. Is there questions from the room? Yes, well, there are a lot of questions. Fauzi was very fast to raise his hand.
Okay. What I have remarked is that all the projects that you have presented here are not operating. Our pilot projects are quite ready to be operated. But hydrogen storage started in 1972 in Teesside. We have different caverns in Texas, the last one of huge hydrogen storage in South Cavern of Air Liquide, of approximately one cavern of around 1 million cubic meter, which started operating in 2016. So we have at least 7 years of experience. So have you any feedback from these experiences in terms of technical point that you have arisen in your objectives and the achievements in terms of the behavior of the compression, in terms of the tightness, in terms of the quality of the hydrogen, in terms of the interaction of the hydrogen with the different materials? Have you any information on this point from these feedbacks? And my question goes to everybody in the room, of course, because myself, I tried with SABIC, who are operating from 1972 in Teesside, and they never came to present us their work.
What I know is that a lot of suppliers got in contact with them, and I think they were able to gain experience. But from Uniper, we didn't get in contact with them directly.
We have the same experience as you have. So it was tough to get, no, it was not possible to get any information other than a visit and looking at the wellhead, see the color. But that was more or less the information that we got. So we had to start more or less from scratch, but with the support that hydrogen storage and hydrogen transport is possible. I mean, there is a industry of hydrogen in Europe, in the Netherlands, of gray hydrogen. So you can transport hydrogen, you can store hydrogen. But for the storage that we want to develop, that's the support of the energy system, where you need many more cycles. So the way of operating is different compared to the Teesside or the storage in the US. So therefore, we started to develop it on ourselves and ask ourselves all the questions. And yeah, more or less started from scratch.
I can just add that we have some very, very rare information from SABIC. They operated their cavern by brine composition. So the pressure variation could be very low in comparison with classical gas cavern operating by pressurization and depressurization. From Air Liquide, we get some information about the size of the cavern, size of the well, and you know that very well. All equipment are gas equipment, natural gas equipment, nothing specific, as we know. And the last things, it's use hydrogen to refine oil and everything, and so the quality of hydrogen is not necessarily the same that we imagine, for example, for mobility or for things like that. But that's all. It's scarce.
I think to complement on this, I think there is still some information on this historical experience. So all this is in salt caverns because it is a historical experience. And SABIC, I mean, we also know that the experience is not race enough. For instance, we know that there is no well completion as we would do now. It was built 50 years ago. So it would not have helped for what was said by Eddy, Miriam, or Grégoire regarding the lack of hydrogen-ready equipment 2 years ago. Even if there is this 50 years experience, it will not have solved all the problems because we don't do salt caverns exactly as we would as we did 50 years ago. And I think there is feedback. There are feedbacks from experiments in these salt caverns. I mean the SMRI report that was published by René Buzogani and et al. Who's here, and where DeepKBB, Geostock, and WSP worked. And at the end, there is a section on this experience, and it's quite complete regarding what you can find on the public domain. And then it's what you can find on the public domain. And One question from the internet audience, and then we go back to the room.
Yeah, so there are a few questions. So a few questions on materials and materials materials compatibility to hydrogen. So I think it's been discussed a lot, and but maybe one subtopic was around the wireline technologies. So wireline tools deployed specifically on the HyStock project. If there is any insight on that.
So we have ran different tools, pressure, temperature, and sonar measurements under hydrogen. It was slightly modified, but relative standard equipment, also for the lubricators that we used. So more or less standard oil and gas technology that we have applied for the hydrogen situation.
Good afternoon, Jean-Claude Joyeux, Air Liquide. I suspect you were expecting my answer to everything was said. I am the bad boy in the room who doesn't want to share his IP and doesn't want to sell the hydrogen. Okay, basically, I agree with you. The point is we developed this technology with Linde and Praxair, by the way, almost 15 years ago. And today, we are not sharing our IPs for other purposes. So it's just a question of competitiveness or antitrust or whatever you want to name it. The point is, I prefer to discuss about the delivery of hydrogen because you are right. A big spot demand today, in particular on New York cavern, but also for test of engines, motors, engines like Safran or planes who want to have huge quantities. And today we don't have the infrastructure in Europe for that. So it's a question of market. It's a question also of cost, price. And that's something we try to catch up. But for sure, those equipments were developed mainly in the US because the market is far above and far forward compared to Europe. Something we need to catch up collectively, and this type of subsidized project is done for that. Thank you.
Thank you. Just a short question maybe to your IP that you don't want to share. What is the IP that you don't want to share? I don't want to ask you to give it, but what kind of IP?
All the question you ask about the type of material, the type of alloys, the consideration of operation, the flexibility of the plant, all those information are operation completion, operation secrets, because it's our operation the last 10 years. So we doesn't want to share our misery or goodness in this type of operation. That's something that I'm not sure those guys, when they will finish, they will share everything.
Thank you. Can you hear me well? Yes. So first I will introduce myself, Carol at Storengy, and regulatory affairs. So I won't ask very specific question, but I would like to know, because most of the time when we talk to policymakers, of course they know that we have large-scale storage, that we have a lot to do, but they seem to be interested in understanding if we can be more flexible than before, if we can cycle more, and to what extent we can accommodate the development of fresh renewable source. Even if you haven't done all the work, because of course it's pilot project, as we need to give them some answers in terms of flexibility, or to what extent we think we are more flexible than before. What could be your answer? Thank you very much.
So for a salt cavern, the flexibility is related to thermodynamic behavior of the gas that you store and the geomechanical behavior of the salt. Well, the geomechanical behavior of the salt won't change with the hydrogen. So from that perspective, the the flexibility is comparable to the flexibility of natural gas storage in a salt cavern.
Yeah, but also if we are more flexible, we have to have more cushion gas, so we get less hydrogen out of the cavern. So we have another amount of hydrogen that we can use for these more flexible cycles.
Because usually you store during the summertime and in withdrawal in wintertime, very easily spoken. But when you think about hydrogen storage, you think about more flexibility, as you just mentioned, like multi-cycles. And then we, of course, need to increase the amount of cushion gas. Yeah. Unfortunately.
Yeah, I mean, I agree. It's a matter of investment. It's a matter of design. But of course, you can do if the market has a need for that. I think it also it matters in what energy system you are. I think the parameters are different. For instance, at the North Sea coast with a wind-dominated energy system versus the situation in Central Europe, in Austria, in Bavaria, for instance, or in Italy, where you have rather a PV-dominated energy future, yeah? Where these seasonal cycles dominate and not the Dunkelflaute.
Yeah, it's a discussion we already have together, but I can share it. In fact, we don't know exactly what will be really the need of storage for hydrogen. Do we use hydrogen as we use gas, something seasonal? Will we really need this very high cycling on a small part? Maybe the idea to have a small variation of pressure on limited quantity of the storage and maybe larger quantity more seasonal. We don't know exactly. So it's a little difficult to answer to this question. Maybe we will have to invent ways to be very flexible by using different cavern and playing with that. It's probably possible to inject in one cavern and withdraw for another one on the same site. That we today we don't do that with natural gas, but technically there is no limitation to do that on another site. To store hydrogen is a way to store energy. We have also to think a way to store the other way to store energy. For example, in electricity, you can store in battery, and for something very flexible on a daily basis, it's interesting. On a monthly basis, the battery is not very interesting, but it's very interesting to store the energy under hydrogen form. For example, it could be a complement, something, yeah, complementary with the battery for daily use, and maybe for something on long time, it's more interesting to have hydrogen storage. But that's right, today it's a little difficult to imagine what will be the real need for hydrogen storage, on my point of view.
Thank you for all the very interesting talks and the insights. I was triggered by some remarks that were made by Uniper and also by Austria about the mining authorities that are also need to learn a lot, and regulations that are not in place yet. Still, you do these pilots, but at some moment you have to scale up. You have to create a full-scale development, and then you will have these authorities also, with you maybe to make sure that these are well-supervised projects and safe projects, etc. How do you work together with these authorities at the moment to make sure that their education levels and their expertise is on par with the projects that you have to develop? So they have to build knowledge as well and develop regulations. Are you involved in that, and how do you do that?
Yeah, I mean, we have talks with them on a regular basis, not only on project level. We try to convince them that we need future regulation, that we need some changes in the mining law and others. Usually it takes a little longer to get amendments there. That's our observation. Yeah.
Yeah, and I think they also did their homework. They realized that that there's a new gas coming, and I would say we develop together sometimes, or there's a problem and we work together on it. And also after a while, the authorities in different areas, they get together and share the results. So I think there's a lot of knowledge sharing now going on, and yeah, it's getting better and better. Yeah, but what I want to say is that we got a lot of support from them. I hope that it wasn't the mean. That you didn't understand that they were that they didn't understand. Yeah, they want us to do the project, and they helped us, and yeah.
Yeah, finally, the enthusiasm we found in the suppliers of wellhead or completion, we have the same enthusiasm also for the administration. They are in between something strange, because hydrogen storage could be something interesting for all the society, and at the same time, it's also a hazard, a risk, and so they are to balance between this risk and advantage. So it's sometimes difficult to discuss, but there are real interest also in the administration to help to develop the storage. We have this experience in France too.
Yeah, and the same in the Netherlands. So the authorities looked over our shoulder when we were executing the pilot project. And I think that's good. Obviously, they also have their own obligation to get knowledge. So there is a separate study initiative by the authorities to gain information. But I guess what will be difficult is once we apply a permit and they have to say yes or no against that permit, it will be difficult for them to value the permit against as there is no existing rules, or there is no existing limits, there's no existing accepted leak rate, for instance, for hydrogen. So when is something good if you have nothing to measure it against? So that will be a next challenge, and I guess that is also a challenge for all of us, for Europe, to come up with standards against you. Things can be tested and can be said this is good or this is not good. So that is the next step.
And what we did, what Miriam showed at the beginning with the timeline, we started with a permitting procedure. We started involving the authorities and informing them about what we plan to do. And also we have several experts that write documents about their expectation of the whole project, and we have the third party involved, the DNV, that is reporting on everything that we do, so that they don't have the opinion that we only as a industry want to do this for our own profits, but also this is really proven. Everything is proven by several experts.
Next question.
Leszek Lankow, Polish Academy of Sciences. I've got two questions, two short questions to Stephan. In your presentation, you mentioned that you store natural gas with admixture of hydrogen. I would like to ask if you plan to increase the share of hydrogen in near future in this admixture, and to what extent? And the second question is, do you have or do you plan to develop a monitoring system in case of hydrogen leakage?
First question, yes, we started with a mixture of 10-20% of hydrogen, and that happened in let's say more than 10 years ago, or the decision for such project happened 10 years ago. And at that time, a lot of discussion was going on how much hydrogen could we add to the natural gas system. Yeah? I think that this discussion somehow declined, and now more and more people are heading for a pure hydrogen infrastructure. So our ongoing project, the project I presented here, is a pure hydrogen project. And to me, it doesn't make sense to check anything in between 20 and 100%. Yeah, I think when constructing a facility, you have to decide. It's not possible to have a facilities designed for any mixture between 0 and 100% hydrogen. So that's our outline for the next thing to check for 100% hydrogen. And monitoring, yes, we do a lot of monitoring in terms of downhole measurements, in terms of pond log measurements, and integrity measurements. What we do not do is let's say scan for hydrogen on the surface. We do not expect to detect anything like that with 100 meters of clay layers. Yeah. So yeah, once the integrity of your well is guaranteed, yeah, surface equipment, of course, you check for tightness there. That's for sure.
We'll take a last question, I think.
Yes, I'm under the impression that there is something not optimized at the European scale, because each of you has to convince its own regular or national regulators. We end up with every TSO building or launching the same pilot, well, excepting for porous media. But basically what we have seen today is the same pilot in salt caverns. So I think it's a pity we are in this situation. It's not a question, well, it's a question, of course.
Well, I do not agree that it is the same pilot. It goes from relative simple to more complicated. The first pilot that we executed was in a borehole with approximately 80 cubic meter of cavern size, where we did 3 cycles. When we look at the HyPSTER project, it's a cavern of 10,000 cubic or something like that, or maybe a little bit smaller, but at least there is many more cycles. When I look at the H2 cast project, there will be maybe between 10 and 100 cycles. So it's more, there is an added value. Not all the projects are sponsored by the European Union. So, I think there is overlap, but the overlap is also there to gain operational experience by the operators. So it's not only to prove the concept of storage, but it's also to gain experience by the operators. So I think there is an added value for many of the pilot projects. And yes, I do agree there is overlap. So things might have been a little bit more efficient, but I would rather look at it from the positive side. And the more pilots are executed, the more experienced is gained by more operators, which makes it more feasible that there will be more projects developed in future.
Yeah, I would say the same. Also, a lot of the suppliers, they realize, okay, there's a lot of music going on, and you need to do little steps to reach the aim, that all of the caverns or all the depleted gas fields or aquifers are filled with hydrogen. And you need to gain the knowledge. So it needs to be done. So I would also agree to see it in a positive way.
I could add that I totally agree with you that there is sort of complementary position of the different projects. And what is difficult with the administration, it's because it's new. If we gain more and more experience from the different pilot, from the different storage, it will be easier and easier for the different administration to know how to treat that because it already exists. They can be confident in this sort of equipment. They can be confident because it's already tested in one pilot. We know another. We have not the same suppliers, for example, for the wellhead, for the completion. So it's interesting for the market because today on the market you can find different suppliers for the different equipment. So it's an interest for all, in fact, and for the administration to gain this experience is also interesting. Of course, for the first one, it's difficult. For the second one, it's a little less difficult. For the third one, maybe, I don't know, in another country. They can discuss between administration. And so with time, it's interesting. And at the same time, it's interesting to have not exactly the same way to arrive to the steel you choose, for example. What is funny is that we don't discuss between the pilot experiment, but finally we all arrive to the same steel, LAT, for example, for the pipes, because we have an analysis and say, but maybe another one say, finally I will take another steel, and we will test that and to have another experience. And what is important is to share, and probably the reason why we are here is to share this experience and to make the other to have this benefit to help the development of the global hydrogen chain.
Thank you for comment. Actually, I would like to see a few more pilots on depleted reservoirs because there the difference is that really every reservoir has a different geochemical setup, microbiological setup, salinity, everything, yeah, and we somehow need a few pilots spread around Europe to really check the potential of hydrogen storage in depleted reservoirs.
Thank you to all the five of you for the presentation of these pilot projects, to all the audience for the questions. So it's the end of the day, first day of the final conference of Hystories. I hope you found it interesting. We will continue that tomorrow. Tomorrow it starts at 9. I mean, conference starts at 9. For in-person people, you can come from 8:30, and you're invited to do so. And so yes, thank you. Thanks a lot.